So let's look deeper into this paper. Let's start from the section that talks about some puzzling experiments. Okay, so they have these algorithms here. Let's go over them to see what they do. The first algorithm is permute algorithm. What this algorithm does is essentially randomly permutes the elements of an array. So we have an array A of size n, so typically n could be big, but they're gonna change n depending doing your experiments. So permute essentially picks a random number, and for every iteration I picks a random number j, and then it will basically swap ai and aj, right? So that's a very simple algorithm. What is the running time of this permute? So this is gonna be O of n, right? Because we have n iteration of the loop and every step is just constant, so that's just simple O of n. Random scan, again, you pick a random permutation, and what you do is that you compute this. So in other words, let me explain what this means. If this is, whoops, can't draw straight lines. If this is your array A, what you're doing here is that you're jumping through A in random order, right? So for example, you access first this, or maybe this is pi 1, this is pi 2, etc. This is pi 3. Instead of scanning the array from like in an orderly fashion, you scan this in random order. This is obviously also O of n, so it's the same. Then you have n binary searches for random position in A, and A is sorted. So in this case, we start with a sorted array. And if you remember, you can, if you have a sorted array, you can actually think of it as a binary search. Right? You have the middle point. You first compare your random position to this. If it's smaller, you go here. If it's bigger, you go there. And then you compare it to the middle of this guy. And then if you go this way, you compare it to the middle of this guy, etc. Each binary search should take log n time. So n binary searches should take O of n log n. So this is n log n. Heapify. If you remember Heapify, it's a process that's used in let's say heap sort, and Heapify is a linear time algorithm. If you remember this, so that's linear time. Heap sort, we've looked at it in the exam before, so it's in log n, but we know that from the lectures that doesn't have good cache behavior because it doesn't respect memory hierarchies. Quicksort is also linear and log n, and sequential scan is linear time, obviously, because you just go through the array. Okay. And over here, they basically explain what I just did. Okay, so if we run these algorithms, let's see which ones should be fast. So sequential scan should be fast. Quicksort should be relatively slow. This should be slow. This should be fast. This should be slow, and these ones should be fast. Okay, so we expect 4 of them to be fast, 3 of them to be slow. And let's see what happens if we look at this in practice. This is the result that they get. I'll just zoom in. Okay. This is quite surprising, right? First of all, we have first of all, we can see that something funny is happening. Okay, before going, first of all, this is running time divided by RAM complexity. So we take the running time that we think the algorithm should have had, divided by the running time that we think it should have. In other words, if it's an n log n algorithm, we divide by n log n. If it's a linear time algorithm, we divide by n. In other words, if our theory is 100% correct, we should see just a bunch of horizontal lines, and we should see essentially constant functions. But that's not what we see. Okay. Some of them are constant. Let's say this is sequential scan, this is constant, so this fits with the theory. Heapify is constant, that fits with the theory. Intro sort, I don't know what that is. Heap sort does not fit with the theory. This is also what we saw in the lectures, but we kind of expect this because we know heap sort should not behave nicely. Random scan doesn't fit, it blows up. And permute also blows up in some really funny way. So we have to explain this picture because this does not fit with the theory. But this does not prove that what they actually want to prove, because it doesn't prove that it's the cost of address translation that is responsible for this behavior. Maybe it's caches, maybe it's something else. So to further prove their case, they need to run more experiments to isolate more factors, because this by itself just proves that the theory is not enough. But we kind of already knew that.